Yes,
Your
welcome.
voice is telling me. You
Uh,
know that there's test today.
I know.
Yeah. So I have just prepared the test paper on the first chapter of 80 marks. I think it is very
Mm-hmm.
easy test paper, and I have given the time 3 hours, but you can finish in 1.5 hours. Tomorrow I'll prepare it on chapter two. Also, you give chapter one different test, chapter two. Is it okay? It will be more
Yeah.
feasible and understandable.
Mm-hmm.
Okay. So I'll forward the second test based on unit one, chapter two tomorrow. Okay. So we'll start with the things. We'll
Mm-hmm.
just revise what we have seen yesterday.
Mm-hmm.
So, for example, 3.3 it was. Yesterday I was having my boards exam of my students in India here. So I was taking class from last 12 hours, and your class was
Mm-hmm.
in the 13th hour of the day. I have taken 12-hour continuous class of different students, 2 hours. So I was very fed up
Yeah.
yesterday, very tired, very
Mm-hmm.
fed up, and I can't explain you. My whole head was paining, and I was very feeling dizziness, very weakness. And in that sense, I took your class because it was not good for canceling the classes as I have cancelled it once earlier. So I took that
Mm-hmm.
in that sense. So what I'll do, we'll just revise what we have seen yesterday. So
Mm-hmm.
I will be comfortable that I have delivered you the whole topic correctly. Okay,
Mm-hmm.
just we will revise the things. Yesterday was very hectic because today was the board's exam, the central board exam of the high school, secondary high school students, that the 12th grade year is considered to be very, what you will say, uh, very important year, 12th grade exams. So it was there. So I was taking, as I take personal tuitions here in India also. So there are around four students. So I have given three hours to every one of them. From morning 7 a.m. I was taking class till evening 7 a.m. I was taking. And yesterday 8 a.m. it was yours class in the 13th hour. So I was very fed up.
Yeah. Okay.
I think unit 2. Okay. So yesterday we have seen that in transforming, achieving linearity, when we were achieving linearity, we have seen that if the graph was for to be in this sense, we either apply cube root to this explanatory variable, or take cube of this this response variable, either take cube root of this response variable or apply cube to this
Mm-hmm.
explanatory variable depending on the data. Yes or no, Zaid?
Mm-hmm.
So what does this do? This non-linear graph, this was a non-linear graph, non-linear. Okay. So when we cubed this, first of all, I'll write the, for suppose it was in y and this is in x. So as it is an increasing graph, increasing order. Yesterday I've told you if it is in this form, okay, the curve is inside, the curves is inside. Then what do we do to achieve linearity? This is a non-linear, so to achieve linearity, we generally take the power of the explanatory variable. Power of
Mm-hmm.
the explanatory variable. We can take any power of the explanatory variable. I suppose that power as p. So when I have taken the power of the explanatory variable, power p of explanatory variable. So when I'll take, so this will form a linear graph. This will form a linear graph. And if I want to, we have seen that if I want this graph to be, this explanatory variable to be in the x form, so what I have to do, take the pth root, of both the variables. So this will be x. This will be the same graph, just what I have done, taken the pth root of both the things. So when I'll take the pth root of x raised to p, uh, pth root of pth root of x raised to p. So this p and this power p and root p will get cancelled, and this will be x. So it is here, this is x. This will also be a linear graph. This will also be a linear graph. Okay. So this is the thing. Either you can do like this or you can do like this. Not a problem. And this equation is represented as y equals to y hat is equals to a plus b x raised to p. Yes or no? Or you can write it as y hat p root of y hat a plus b x. Yes or no, Zaid? We have seen
Mm-hmm.
yesterday. Is it correct?
Yeah.
Yeah. So this was the thing, or either this was taking the powers of the explanatory variable. First, in first example that we have seen, we were taking the log when it was the graph was. This is the second type. In textbook, it is the first type. We are taking if it is like this type, the curved is inside. The curved is inside. See here, this is non-linear. Non-linear. Okay. So what do we do in this
Mm-hmm.
case? This is y. This is x. This is y. This is x. Okay. So when I'll take the log of the explanatory variable, log of x. Okay, so what it will do, plot like this. Yes or no, say
Mm-hmm.
it will be linear. Or else I can do, I have taken likewise y equals to log x. So when I transform, there is the base is e, and you know that when you transform this, it is e raised to y equals to x. Yes or no?
Yeah.
Yeah. So it is like this. So we can draw this in another sense as well. If we'll keep x as it is, so we need to take the exponent power of y. Either of the thing we can do. Likewise, you can see here. Here, what we have done, same thing. We can take the pth power of this, and then if we want to keep the x in the same diameter, so we can take the pth root of both the variables. Here also same thing we have done. If we want to keep both the things in that sense, so what we have taken, take the eth power or eth power of exponential power of this. So e raised to y equals to a raised to log base e. Both the bases are e, and you know if e raised to log is the inside one, so it is e raised to y equals to x. So we can plot
Mm-hmm.
this. This will also be a linear graph. Is it clear, Zed? This thing also?
Yeah. Yeah.
Yeah, linear. So we have seen different examples yesterday. We have seen, we expect, we have read all these things. We have seen this example. See, in this also, he was yesterday as I was very tired, so I didn't explain you this. This was an pizza example. For suppose we are plotting a pizza, so area we know area. That means the amount what we are going to eat is considered about the area. So area will be equal to pi r square, correct? So pi r square and the
Mm-hmm.
diameter was x. So what will be the radius? So radius will be x by 2. Yes or no? So when we'll solve this pi into x by 2 ka square, square of the x by 2. So it is pi by 4, 2 ka square of 2 is 4 and it is x square. So what we have seen here that pi by 4 is this constant a slope we can take, or we can say b, as we are taking b attached with this, and this is x square, and it is this is for suppose y, which is the area. Okay, so we have seen that area equals to the amount that we are eating. The amount that we are eating is the y, eating amount and the base, the inch, pizza inch is the x. So pizza inch is the x. So when we'll plot the scatter plot of the regression line of this, then it will be linear. Yes or no? This will be
Yeah.
linear. That's the thing. Where if we are plotting in y and x, so of course it will be non-linear. It will be non-linear. So depending on the case, what we can say, depending on the domain, depending on the depending on the domain, we have to plot the graphs. We have to plot the graph. Means domain, or you can say dimension of the things that we are calculating. Dimension of the things that we are calculating. Okay, we are calculating the amount that we can eat. It depends upon the inches of pizza inches, correct? So we need to calculate the things. Is it clear, Zaid?
Mm-hmm.
Yeah, so it is clear. Okay. So, this is the thing. Okay, so now this example we have seen. See, this was between the, what you will say. Imagine that you have been put in charge of organizing a fish tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You are also aware that using delicate scales to try to weight a fish that is flooping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length and of the fish while on the boat. What you need is a way to convert the length of the fish to its weight. You contact the nearby marine machinery laboratory, research laboratory, and it provides reference data on the length in centimeters and weight in grams for Atlantic Ocean rockfish of several sizes. Here is a scatter plot of the data. So you can see here the scatter plot that he has plotted the scatter plot of weight with length, but it is non-linear. Yes or no?
Mm-hmm.
The data. But what
Mm-hmm.
we need for prediction of something, we need a linear thing. Yes or no? So we have seen
Yeah.
that if the data is in this form, non-linearity, we generally take the power of the explanatory variable. Correct, Zaid?
Yeah.
Yeah. So when we have taken the power of the length, we can do this, that we can take the cube root of the weight also for plotting this. It will be the same. Yes or no?
Mm-hmm.
Yeah. So this example we have looked yesterday. Just a minute, I'll drink some water. Okay, I'm back. So we'll take on this board this one.
Mm-hmm.
So see, he has taken the weight here, weight it was, and it was length. So it was coming non-linear. I've told you when the curved inside, we generally cube the things. So what we'll do, generally we'll cube only. So it will become like this when we take the cube of the length with the weight. So what we can do eitherwise, he has telling us that. So we can take the cube root of length. So the cube root of weight will also be a linear graph. Is it clear?
Mm-hmm.
Yeah. So this is was the thing. See. Okay. So next thing is simple. We have discussed this in our yesterday. So this was the thing. So he's telling that transforming with logarithms. So when we are transforming with logarithms, we need to, if we are applying log on the explanatory variable, so we need to apply the log on both the sides. Okay? To achieve a linearity from a power model, we apply the logarithmic transformation to both the variables. Here are the details. A power model has the form y equals to a into x raised to p, where a and p are the constants. Correct? Taking the logarithmic on both the side of this equation using the probability of logarithmic, we get, see, when we take the property, when we have the linear equation as, when we'll consider y equals to a raised to xp, for example, he has taken xp only, no? It's xp. So when we'll take log on both sides, log y equals to log of, and you have learned the properties in your previous classes of log, or shall I explain you what he is doing? What is the case?
No,
You know
I
the
learned it.
properties of log?
Mm-hmm.
Yes or no?
I said yeah. Yes. Yes.
So we know that when there is a multiplication, what does the log function do? There is a multiplication in between. So when we'll separate, it will turn this multiplication into addition and separate.
Log A
Uh,
plus
both.
log
So what?
okay, log Y equals to
Correct.
log A plus P log X.
Correct. And this power also comes on to the back of log, and this is the thing. So when we are applying log, he's telling us that it applied on both the sides. So the transformation shows that taking the logarithmic on both the sides result in a relationship between log x and log y. So when we apply log and log on both the sides for a non this for a data which is linear, which has become which had become linear due to taking the power of x. So when we apply log on both the sides, this data between log x, this will be log y and log x. This will also be linear. Logarithmic transformation was a different thing here. See in the first case. It was here, correct, here. So what we had taken only log of the explanatory variable, as we are taking log of the power, we are taking the power of the explanatory variable. But in this case, what we are doing, we are transforming the line of the power variable, power of the explanatory variable to the log form. So he's telling that if we apply log on this also, it will be a linear model. Okay. So moving forward. Okay, so look carefully. The power p. Note you can use base 10 logarithms or natural base e logarithm to straighten the association. So we can use any natural logarithm as well as the log to the base 10 also. Look carefully. The power p in the power model becomes the slope of the straight line. So you can see here it has become the slope. Yes or no? See, this is log a is
Mm-hmm.
the constant. What you will say the y-intercept. Log a will be the y-intercept, and this as it is with the explanatory variable, and we know that the things which are attached to the explanatory variable which are in the multiplication of it, it's called as the slope. So the power becomes the slope. Yes or no? The more
Mm-hmm.
power we apply, the more straightened the line will be to the x-axis. So if a power model describes the relationship between two variables, a scatter plot of the logarithm of both the variables should produce a linear pattern. So when we have to apply log on both the variables, not in every case, but when there is a model of power model where we have taken the power of the explanatory variable. So if we take log on both the sides, so this will also give a linear model. If we plot the data according to this, if it is getting very complicated for taking the power of each variable, if we plot with this also, it will give you a linear model. Is it clear what I'm trying to explain?
Mm-hmm.
Yeah. So see here, see here in this thing. Here was the data with weight and length, weight and length, weight and length, correct? Weight and length. So we have seen that we have taken the length cube in the previous case to achieve linearity. Now what we have done, that taking the log on both the sides. See, log. So what will be the equation? What will be the equation? See, I'll take this graph on this. Just a minute. Okay. So we have seen that when we had plotted the line, it would be generally y equals to y hat. Y hat, that's the weight. Y hat for weight. I write here weight. Okay. Y hat equals to for this previous graph I am telling you, if we take the log cube, so it will be something a plus b x cube. Yes or no, Zaid? Length
Mm-hmm.
cube. This
Yeah.
x is length. So when we'll apply the log on this data, so what it will be, log of weight. Log of weight, that's y hat. Log of weight, that y hat, it will be equal to, okay, so it will be constant, that's the this, correct, this constants minus
Mm-hmm.
1.899, minus 1.899 plus 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 p. What is the p that we had taken? 3 into in the case 3 into it will be log of length. So log of length is 3.04942, 3.4942. This is the thing. So we'll see is our answer correct or not. So this will be, see here. Oh, 3.04942 into length. 3.04942 into length. Okay. It will be, the slope is that. So see here, 3 point, this is the constant. Already has taken the log of the constant, so we are not applying log, and this is the slope, correct? So it will be 3.04942 into log of length. Is it clear?
Mm-hmm.
Yeah. So that's the thing what we need to do. Okay. So it is the this line, log y, log weight. He has just changing into a simple. We are calculating for a fish of 36 centimeter length. This was the third C question. Okay. Now we have, I think, he is explaining how do we find a power model for predicting y from x. So you have seen for doing various calculation of a power model, we generally take log on both sides. I'll write it here. When note, I'll give you in the form of note. When we are plotting a power model for a non-linear data, so it is convenient that we apply we apply we apply log on both the sides so our calculations and predictions become more easy and accurate. More easy, more easy and accurate. Do you know how to use a log table? Is
Mm-hmm.
have is is it taught in your school how to use a log table for calculating the value of log? See here,
No,
he's doing here least square regression line for
we
weight.
use a calculator.
Yes, for different things he has shown here.
We usually don't use log. We
So,
use
okay,
just the regular formula.
oh, so this is the thing. This equation is now familiar with the form of the model. Okay, where P and A is different. Okay, so we were about to calculate the A. So as he has taken the that block to the base 10, so we have taken the minus 1.899 in the power of 10, and then we had calculated. See, it is in this form. I'll take this. I'll explain you what he's doing here. It is very important. Okay, this is generally this form. This form was our, we had weight cap equals to minus 1.89940 plus it was 3.04942 log of length, correct? But we need to take,
Mm-hmm.
for suppose this will be log a, yes or no? As we have written in the previous equation, log y equals to, it was log of weight, log of w cap, which will be log y, this will be log a, plus this will be p, correct? Log p na nahi, p, and this will be log of length. So what we need to do, we need to calculate the values of a and p. So what will be here? Log a equals to log to the base 10 he is taking, a equals to log to the base a 10 equals to 1.89940, correct? So for suppose it is
Mm-hmm.
log a, correct? We need to calculate the value of a. So what it will be? This shifted to this side and this takes it into this power. So it came to be
Yeah.
here. See this minus, it was minus, correct? It will be minus and minus. So it came it out to be negative power of 10. It came out to be 0.00126. And when we take the power of the whole thing, this all shifts into power. 10 power 3.04942 into log of length. Log of length. So it came out to be, see here. This is the thing. So it was when we used to write now y equals to y cap equals to a x raised to p, correct? So we are writing in this form. So it will
Mm-hmm.
be weight cap without log, it will be equal to 0.0126 into x. What is x? It is length of power. It will be power uh, 3.04924. Is it clear?
Mm-hmm.
Yeah. So that was the thing. Please try to explain. So see here, he has taken, see this was the thing that we have done. So it has changed into linearity things. Okay. Transforming with logarithmic. Now we have seen that transforming with logarithms, exponential models. That was power models. Now we are seeing with exponential models. So we can see here it is time versus balance. So when we take the log on both the sides, it generally goes into a linear model. So I think this was the example that we have seen. So it was this. So see here, what he has taken. He has taken the log of the transistors here, because why transistors? Here we'll see what is the question. So Gordon Moore, one of the founders of the Intel Corp. So what we'll see first, we'll see what he is trying to explain here. So a linear model of the form y equals to a plus bx, the value of y increases at a constant rate of x increases. The slope b describes the constant rate. Oh, it's all the things that we have seen earlier. So he has trying to explain that only, that if it is a power model, so how to convert it into an exponential model or a log. You know, a log and log and exponential are inverse of each other. Are inverse of each other. Do you know that?
Mm-hmm.
Yes or no, Zaid?
Yeah.
Yeah. So for suppose I'm writing log to the base 10 x equals to y. So I can write x equals to 10 raised to y. Or this, see, this is in exponential form, and the same thing, it is vice versa, inverse of the log and exponential. Exponential means any constant raised to the variable, it is called as the exponential. That's the thing. So now he has given
Mm-hmm.
the example that we have the data of the microprocessors, in which year the microprocessor and the year and the transistors produced that year. What is time? That Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 the number of transistors on an integrated circuit chip. You know that in he's trying to explain that there is an integrated chip that is known as IC. In 2000, 1965, in this small chip, which is in our phone, in this chip only 2500 transistors can fit. Transistors can be fitted in that time, in 1965 or 1962. But at that time, the scientist told that in every coming 10 years the number will be doubled. The number will be doubled. Okay. And in the recent sales show of Apple, he had declared that in Apple phones, there is a transistor with 10 million transistors in that small chip, 10 million transistors. So this fitting of the transistors in the small chips. There are 10 million transistors in one small chip. So this is the exponential form. Where is 2500 and where is 10 million? Yes or no?
Mm-hmm.
So this was the exponential increase in the research of the transistor. You can see here, this in 1971, there were 2,300 transistors which was fitted inside. In 1978, it became 29,000. See what's the difference? How much is the difference in 1974 and 1978? And in 1978 and 1982, every 4 years, exponentially it is increasing. It is getting doubled in the sense. And now in 2016, how many transistors were there, Zaid? It is around, I think, 7.2 million. Yes or no?
Mm-hmm.
Yeah. So that's the thing. So when we have plotted the things, it is non-linear. So for becoming it linear, what we have done? So we have applied ln as transistors. Transistors was increasing. Okay. As the year proceeds, transistors increase. There is no, for suppose, independency and dependency on the variables, but transistors, as years proceeds, so transistor increases. As year proceeds, transistor increases. We cannot generally give that here is a dependent, here this transistor is an dependent variable and here is an independent variable. In general, it does not imply that. It depends upon the research. But here from the data, we can say it. Correct. So what we have plotted? We have plotted the data with dependent variable. We generally put dependent variable here, but he has taken the dependent variable transistors here, and the here is here. So what we have done, we have applied ln on transistor. So first it was a non-linear graph. When we have applied ln, so it had become a linear graph. You got that?
Mm-hmm.
Yes. So it can be generally seen. He has made the equation and all that. We have seen that yesterday. So we have taken see the log changing this expression, which was in the form of ln. See, we have not taken log on both the sides. Just we have taken the log of the what you will say. response variable. Yes or no, Zaid?
Mm-hmm. Yeah.
Yeah. So changing this ln into the exponential variable, we shift this e, and this whole will go into the power of e. Correct? I'll take this on board. He's just showing us the transformation, what calculation goes behind in the data. So you can see here, see, we have applied ln. We have applied ln to y. Okay, only y. We have not applied ln to both sides. Just we have taken the log of the response variable. So it was 7.2272 plus 0.3542 into years. Correct. I want to change this. I want to remove ln. So it is here. The base is e. So I have told you where we take y. So e goes into the power of all, taking all the things into power, 0.3542 into y. Correct. So it will be shifted as e 7.22. Powers are in addition, so it will be gone into multiplication when we split it. 352 into y, 3542 for suppose. Correct. So this is the thing. So we'll calculate the value of this. So it is for suppose he has taken 1376.4 and this is the value of this. We can write it as years it is. So it is 1 point, this value, this value is 1.4250 into y. Correct. So it is of the form, if we simplify, y equals to, so y equals to a into what you can say, uh, p raised to y. So what is this? Is the explanatory variable. This is the a. See here. Yes. Yes or no, Zaid? You got that?
Mm-hmm.
Yeah.
Yeah.
Okay. So putting it all together, which transformation should we choose? The question comes, which transformation to choose and when to choose. Okay. So he has given how to choose a model. When choosing between different models to describe a relationship between two quantitative variables, choose the model whose residual plot has more random scatter. If there is more than one model with a random scatter residual plot, choose the model with the largest coefficient of determination r square. So what is telling us? Just a minute, I'll drink some water. Hello. Okay. So he is telling us that depending on the scatter, depending on the randomness in the data, depending upon the randomness in the data, we calculate the coefficient of determination. That's the R square. Then we see the lower the see when there is a point value, when there is a point value for suppose R square is 0.39. So when we take the square of this value, it becomes more smaller. Yes or no?
Yeah.
Yeah. So depending on that thing, how much is the value of R, the correlation factor, we take the power to make them big. If there is more than one model with a randomly scattered residual plot, choose the model with the largest coefficient of determination. So we'll plot different models with x square, with x cube, correct? Fill with log x, taking different things, and we'll calculate R square of all the models and see in which R square is more. We'll choose that model to be more accurate. Did you got that?
Mm-hmm.
Yes, that's the thing. How to choose the model? Which model, which power model, or the log model, or the exponential model that you have to apply? You have to choose. It depends upon the R square. Okay, so that's the thing. So see, he's given one more thing here. He has given the residual plot of this. Now we what we need to do is write the equations and all. See, okay, we'll do this question. It is more. How is braking distance for a car related to the amount of tread left on the tires? Research collected data on braking distance for a car making a panic stop is standing water. along with the tread depth of the tires. Here is a linear regression output for the three different models along with a residual plot for each model. Model 1 is based on original data, while model 2 and 3 involve transformation of the original data. See, here it is model 1. So what you can see in the R square value, how much it is? 0.822. Yes or no, Zai?
Yes.
Okay, and in this model 2, when we had applied some of the model transformation, what is the R square value? 0.999. Yes or no? And
Yes.
in the third model, it is 0.886 when we had applied the transformation. Yes or no?
Yeah.
Okay, so which model will be more accurate? Which model you will choose? Model 1, model 2, or model 3? Which has more R square value? Which has more R square value? Model 2. Yes or no, Zaid?
I think model one because it's almost it's closer to one.
Okay, so we'll see the answer. Which model does the best job of summarizing the relationship between tread and breaking the distance? Explain your reasoning. So because the model uses x length log of tread depth and y log of braking distance produce the most randomly scattered residual plot with no leftover plot pattern, it is the most appropriate model. Note the value of R square is
Mm-hmm.
also closest to 1 for the model that uses x equals to length tread and braking distance. I've told you. See, in model 2 it was. Yes or no? See, I've told you now. The best model depends upon the R square value. See here. What is the R square value? 0.99. So see the R square value of this. It is less than 0.99. See the R square value of the original model. It is less than 0.99. Yes or no? See here. Yes or no, Zaid?
Yes, I agree. I agree.
So this R square value is the greatest in this model. So with ln with thread, what we have applied to ln with thread and ln to the braking distance also. See braking distance and ln with thread. So this is the best model. Applying log means that it is a power model. Yes or no? Applying log means he has taken
Yeah.
the power model there. Yes. So that is the thing. So B question was use the model choose in part A to calculate and interpret the residual of the trial with the thread depth with 3 by 2 inch, and so we have to make a regression line on the model 2 that we have choose from this data generally, and predict the value of the given things. So you will do it at home. Okay, it is very easy
Mm-hmm.
depending on the calculations. So this is also one example and the software. And see, we have now completed. I will be more relieved as I have explained to you each and every example, going with more depth. Have you enjoyed the session, today's session, as it was?
Yeah.
Yeah. So as it was more expensive, as I was tired yesterday and was not able to deliver the 100% of my knowledge, so I thought that
Mm-hmm.
deliver once more the same topic. So you can do this exercise, and you know today is your test on based on the chapter one. I have prepared the paper. Chapter two,
Yeah.
I'll give you the test tomorrow. Okay. Then we'll finish both chapter one and chapter two. Means we'll finish the test on unit one by tomorrow. This is the half test as it is includes only questions based on chapter one. Okay. So now we'll start
Okay.
with chapter 3, it's wrap up. Okay. You can practice different questions from here. Is it clear, Zaid?
Mm-hmm. Yeah.
Okay. For now, it's the main thing that we are going to see here. Chapter 3 review is there. Now we'll see review exercises also there. It is also very interesting review exercises.
Mm-hmm.
I'll give you the introduction of that. We'll starting with unit 3 or unit unit 3, and it's all about collecting data. Now, Zaid, we have seen that we were making different observations on the data that we had collected. What we were doing generally, what is statistics, collecting. We have not seen collecting for since till now. Okay, this is
Collecting
left
and
over, but we
analyzing
have
data.
seen, yeah, descriptive one,
Yeah.
analyzing one, correct? Yes or no?
And
Analyzing one, and also the prediction part. True, when we have trained the
mm-hmm.
models by training models, yes or no? By training the regression
Mm-hmm.
models and all, we have seen prediction, analyzing, and descriptive stats. Descriptive stats I've told you mean, median, mode, range, standard deviation, variance, what you'll say, then variance and or something more was there. Then correlation when there are two data, quantitative data related. This was all descriptive stack. Then we have analyzed it, analyzed by different graphs, that the bar plot, scatter plot, dot plot, stem plot, pie chart, bar graph, histogram, frequency curve. Yes, we have seen all the this. And in the previous chapter, we have seen prediction by training models. Yes or no?
Mm-hmm.
This was all the things in general that we have seen, but we didn't give a question. We didn't give a question that where the data is coming from, where the data is coming from. We didn't give a question to that fact. Correct? So now we are
Mm-hmm.
going to study how it's coming from. Now we are going to study that how statisticians collect data. Collect data. There is millions of data available, but what will be the best thing and the best way? Best thing, best thing, and the best way, and the best way to collect the data. To collect the data. So there are so there are different techniques, different techniques for collecting a data. For collecting a data, I'll give you an example. We have seen the example of the hand span versus the number of candies that will fit in the hand span. We have seen that as the hand span increase, the number of candies increase. But we have done one calculation for a hand span of 10 centimeter, and the output came out to be -6. Yes or no? We have seen that example in the previous class.
Mm-hmm.
Yeah. So that hand span was 10 centimeter, and the prediction of that, when we were predicting based on the regression line equation, it came out to -6. Then what conclusion I had given that time? That the data was all
Mm-hmm.
for the hand span, or for the hand span greater than 14 centimeters. That means that the uh, the person was collecting the data, the person who was the person who was collecting the data didn't took the sample of took the sample of didn't took the sample from small children. Yes or no? That's the reason it doesn't have any data point with less than 14 centimeter, with less than 14 centimeter. So the data had been collected for all the adults, so that's the reason it was inconsistent. The value of it was inconsistent. So for different observations, for different training models, we require, that time I've told you, for different training models we require different samples. So it depends upon what the person who is collecting the sample, on what basis he is collecting, on what basis he is collecting. So the person was collecting the data for the hand span. He collected the data only of adults, and he didn't took the small children or the teenagers, and he didn't took the teenagers into consideration. So when we were when we were measuring the prediction of the teenagers hand span, it came out to be incorrect, very incorrect. Why incorrect? Because it was in negative, and number of candies that a hand can hold, it cannot be negative. It is either zero, it cannot be zero also, but it is always greater than zero. So that's the thing. So we will see the introduction of the topic, sampling and surveys. Then how what are the different methods? I have told you that the population is very big, in millions or billions you can say. But what do we do? Select a small part of it. For suppose I'm selecting this part of the population. This part of the population is known as This part of the population is known as sample. So there are many samples in the population. 1, 2, 3, 4, 5, 6, 7. See? So which sample to choose? Who will explain us? This chapter, collecting data, will explain us. What are the different sampling techniques? This will explain us different sampling techniques. Different sampling techniques based on the domain information. Based on the domain information. Based on the domain information. So it is very important that to look onto the domain and collect the data. Yes or no? So there are different sampling techniques there. Techniques. There are different sampling techniques. We'll see there are basically on the top there are four. We'll see the names of it tomorrow. Then we'll see different experiments that is used using studies wisely, and then there will be a wrap up. So see, introduction, you can hardly go a day without hearing the result of a statistical study. Here are some examples. So he has given some examples there. So this was the thing, and sampling and surveys is there. So this was all the thing that was in this chapter. So I think we'll start the chapter tomorrow. Is it okay?
Mm-hmm.
Okay. So you revise for your test. When shall I transfer the question paper? At what time? So that you'll give. At what time you'll give the test?
Mm.
Okay.
I'm
I'll
not sure.
transfer the question paper to your mom. You discuss with her, and then she'll transfer to you. Is it clear?
Yes. Mm-hmm.
So we'll stop here. Okay. Was it today's
Mm-hmm.
meeting interesting?
Yeah.
Okay. So Assalamu alaikum. You can end it. Okay. You can end it
Mm-hmm.
here.
Assalamu
Assalamu
alaikum.
alaikum.
Alaikum salam. Mm-hmm.